You've probably seen this photo of the solar system many times. Many of you even know that it's an inaccurate display of our solar system. The size of our solar system and the positions of the planets has been modified. This leads us to ask, why aren't our images of the solar system to scale? How can we create a scale model of the solar system? And how does it relate to Calculus 3? Images of our solar system aren't to scale because the solar system is really big, and that makes it difficult to visualize. In Calculus 3, we represent locations and objects in three-dimensional space, which lets us describe planets and their orbits mathematically. What do we mean by space is really big? We mean the distances between the Sun and Neptune, the furthest planet in our solar system, is an average of 58 million kilometers or 36 million miles away according to NASA. Now compare that to the diameter of Mercury, the smallest planet in our solar system, which is roughly 6,792 kilometers. The distance between the Sun and Neptune is over 920,000 times the diameter of Mercury. Second, if we know that two planets may be at opposite sides of the solar system, the image would need to double in size to include them at their furthest distances. With that magnitude, it would make Mercury and most of the other planets not visible to the eye when looking at the solar system as a whole. Keeping this in mind, our aim was to create a scaled-down view of the solar system, to view the planets' relative sizes, and to demonstrate their orbital paths of the planets. To do this, we used implicit surface equations for spheres, vector translations, and parametric curves. In Calculus 3, a sphere centered at ABC with a radius r is described by the implicit surface equation x minus a squared plus y minus b squared plus z minus c squared is equal to r squared. Using measurements provided by NASA's website, we created the equation of a sphere to represent the Sun centered at the origin, where the measurements are using gigameters instead of kilometers, which are units of 1,000,000 kilometers per gigameter. Building on this concept, we created equations for each planet, where x minus d squared plus y squared plus z squared equals r squared, where d represents the distance from the Sun and r represents the radius of the planet, still in gigameters. The planetary equation used to describe Mercury in this manner is x minus 57.9 squared plus y squared plus z squared equals 0.00244 squared, again using gigameters as a unit of measurement. As you can see here, we have a full list of diameters and distances from the Sun for each planet in kilometers. So, converting to gigameters, we have the equations to represent each planet. Notice how the distance between each planet to the Sun is significantly larger than its radius, demonstrating why this representation of the planets is effective. Next, we modeled each planet's orbit as a perfect circle centered at the Sun, which we placed at the coordinates 0, 0 on the xy plane. Each planet orbits the Sun at some average distance d, so each orbit can be described by an equation of a circle, x squared plus y squared equals d squared. To stimulate motion of the planet around the circular path over time, we rewrote the circle using parametric equations. X equals the cosine of t and y equals the sine of t, where as t changes, representing time, x and y trace a circular path around the Sun. This keeps the planet at a constant distance d from the Sun while moving around it. Since a true-to-scale model makes the planets nearly impossible to see, we created an additional representation. Specifically, we replaced the actual distances between each planet with equal spacing of one Earth's diameter, or 12,756 kilometers away from each other. This version and representation of the planet sizes allows us to display the Sun and all the planets in one single frame where their sizes can be compared meaningfully. Thank you for watching our video.